Hi, this is Chunxu Tang from Twitter. Today, I want to present about our work, forecasting SQL query calls at Twitter, which is about how we have used machine learning techniques to help us to predict the query resource usage of each SQL query. Generally, there are three sections that I would like to cover today. In the first part, I would like to talk a bit about the overview of the SQL Federation at Twitter. And then in the second section, I want to talk about how we have used machine learning to forecast the SQL query cost. And then finally, I want to share some conclusion and takeaways about our project. So let's begin. The very first section is about the SQL system at Twitter, which contains a long path pursuing high scalability and availability. In this slide, we have put some basic statistics of the SQL system at Twitter. For now, there is around 10 petabytes of data scanned daily in the SQL system, and the system has more than 3,000 compute workers, and more than 10 million queries have been handled in the SQL Federation system. And then finally, the SQL system is built on top of Presto, which is a very popular distributed SQL engine. And here are some use cases of the SQL system at Twitter. There are mainly two perspectives, interactive analytics and ETL or schedule jobs. For the interactive analytics, for example, some users would like to use the SQL system to do some business intelligence tasks, or some users would like to query the SQL system to get some data results and then create some dashboards. Or even some users would like to use the SQL system to help them debug their programs. And for the second use case about schedule queries, we find that at Twitter, there are lots of users who like to run their queries daily or hourly to fetch the data results. And here is the overall design of the SQL Federation system at Twitter for now. At this time, Twitter has adopted a partly clouded strategy, which indicates we are migrating some on-prem workload to the cloud environment, aka the Google Cloud Platform at Twitter. So we have evolved the SQL system into a hybrid cloud SQL Federation system, which is across both the on-premises data center, aka the private cloud, as well as the public cloud, which is the Google Cloud Platform. And here is the architectural design of the hybrid cloud SQL Federation system. On the left side, there are notebook or BI tools. Those tools can send some queries to the SQL Federation system, generate first to the router. And the router will forward those queries to different SQL engine clusters on premises or in the cloud. At the same time, the router will talk with a query cost prediction system, which is our concentration in this presentation today, that where we have used the machine learning techniques to help us to solve the problem. And the query cost prediction system's purpose is to provide a rapid estimate of the resource usage, like the CPU usage and the memory usage of each SQL query, and return the result to the router for query scheduling or scaling. And for those SQL engine clusters, those clusters will communicate with data storage and metadata storage to fetch the query results and return them to the front-end tools. So that's the overview of the SQL Federation system. During the maintenance and the development of this SQL system, there are some issues that we have observed without query utilization prediction, and we would like to share those issues here. For example, the first one is that query scheduling requires an estimate of the immediate workload in the SQL system. We have observed that some resource-consuming queries can easily occupy most resources in a cluster in as short as 10 seconds. The second point is data system customers would like to know the resource consumption estimation of their queries. From our observation, we find that some customers would like to know about, say, how much CPU time or how much memory that their query may consume. And they want to know this kind of information beforehand. Finally, the elastic scaling also needs query resource usage forecasting. Because of the rapid impact of resource-consuming queries, the SQL system needs to scale ahead of the actual processing of the queries in a SQL engine. And we have also found that we cannot directly apply pre-existing DBMS approaches to resolve the problem. Those pre-existing approaches usually use query plans generated from SQL engines. But you see here, we would like to estimate the resource usage before the actual processing in any SQL engine. So this approach needs to be SQL engine agnostic, needs to be independent from any SQL engine, right? So that's why finally we turn to use machine learning techniques to help us to build such kind of prediction. So that's the second section I want to cover today, which is about like how we have used machine learning techniques to predict the resource utilization of a SQL query. And here is the overall design of the SQL Federation combined with the query cost prediction system we have built at Twitter. So for each query processed in the SQL Federation system, it will generate a piece of request log, which will finally be stored in a central storage. And then our SQL query cost prediction system will use these query logs to train some models and for serving the models. From our observation, we find that the logs in the latest 3 months can be a good indicator for the model training. For such a typical workload usually contains around 1.2 million records. And then the training cluster will use these request logs for training. There will be several steps here in the training cluster, such as data cleaning, data discretization, feature extraction, model training, etc. And finally, we will get two models, one for model time, a CPU time, and the other for peak memory bytes. And then those two models are stored in a central model repository. And then we have a serving cluster. This serving cluster will provide online prediction service by fetching the CPU model and memory model from the model repository. And it provides real-time prediction for CPU time and peak memory. So that's the overview of the query cost prediction system. And with this system, that we would like to build a machine learning pipeline to resolve the problem, right? So here, I would like to drill down into the machine learning pipeline to see how we have built different steps into the whole pipeline. In the very first step, we would like to do some data preprocessing for the training dataset, aka the raw logs, that we have applied data discretization and cleaning here. For the data discretization, it indicates that we transform the continuous data, like CPU time or peak memory bytes, into some ranges. In that case, we convert a regression task into a classification task. So why we did this? There are two reasons. The first one is that we find that customers don't care much about the accurately predicted value. They don't care much about whether their queries will consume, say, 1 hour CPU time or 1 hour and 1 minute CPU time. But generally, they want to know whether their queries could be really resource consuming or can be a lightweight query. Another is for query scheduling and scaling. It doesn't require an accurately predicted value. Instead, it's mainly would like to know whether this is a resource consuming query or this is a lightweight query or medium resource consuming query. So that's why we put the CPU time and peak memory bytes into 3 ranges. For the CPU time, the ranges are 0 to 30 seconds, 30 seconds to 5 hours, and more than 5 hours. For peak memory bytes, the ranges are 0 to 1 megabytes, 1 megabyte to 1 terabyte, and more than 1 terabyte. And why we select those ranges? Here we have 5 hours and 1 terabyte selected as the boundaries for resource consuming queries. This is because those two values are some previous threshold in our system. So those are boundaries for resource consuming queries. And then for the CPU time from our operational experience, we select 30 seconds as the boundary for low CPU resourcing queries and medium resource consuming queries. This also helps us capture the large proportion of queries that are in the range 0 to 30 seconds, which contains more than 70% of total queries. By contrast, only 1% of queries fall into the range of 30 seconds to 1 minute. And for the peak memory bytes, we find that the distribution here tends to be more evenly distributed compared with CPU time. As a result, we generally evenly categorize the queries whose peak memory byte is lower than 1 terabyte. So we select 1 megabyte as the boundary for low and medium resource memory consuming queries. So that's the ranges that we have selected. And then after the data cleaning, we split the training dataset into split the dataset into 80% training dataset and 20% testing dataset. And then we would like to extract features from the datasets. Here we evaluated 2 different approaches, word frequency and TF-IDF, term frequency, inverse document frequency, which are 2 popular approaches in natural language processing domain. And those approaches help us to extract features from plain SQL statements. This indicates that our approach is independent from any SQL engine. It doesn't need to have any query plans generated from these query engines. Instead, it only uses the plain SQL statements to extract the features, which is very different from any prior work. After the feature extraction, we'll do some model training here. And we evaluated 3 different classification algorithms: random forest, XGBoost, and logistic regression. And for the model evaluation, we'll first transform the 20% testing dataset based on our vectorizers trained from the previous step, and then we'll evaluate the models trained. And this slide shows some results about the evaluation of the overall accuracy of the CPU model and the memory model. Because we evaluated 3 different classifiers: random forest, XGBoost, and logistic regression. At the same time, we evaluated 2 different feature extraction approaches, word count and TF-IDF. So in combination, there are 6 options here. And overall, we find that XGBoost with TF-IDF approach outperforms other approaches regarding CPU time prediction and peak memory bias prediction. But here, we would like to say that accuracy is a pretty good metric to evaluate a model, but it is not the only one. Especially considering the ranges for the CPU time, there are some imbalanced classes there. So overall accuracy won't be enough to evaluate the models. So additionally, we also introduced the evaluation of precision and recall for the XGBoost with TF-IDF approach. That we especially evaluated the precision and recall for each range of CPU time and peak memory bytes. And we especially concentrate on the results consuming queries because those queries have a large impact on the overall SQL federation system. And from the results, we find that the precision and recall is also pretty good for this approach. Like say for the CPU time, the CPU consuming queries whose CPU time is larger than 5 hours, the precision is 0.96 and recall is 0.95. For memory consuming queries, the precision is 0.97 and recall is 0.98. So in summary, we think that XGBoost with TF-IDF is a pretty good approach for the results usage prediction. And then after the training and evaluation, we'll do the model serving that will real-time serving the CPU model and memory model for CPU time and peak memory bias prediction. At the same time, we also observed a model decay issue in the online environment because of concept drift. This indicates that there are some unseen features generated in the online environment which haven't been captured by our models trained offline. So in that case, sometimes we'll need a model retraining. On the right side in this slide, we have put some diagrams to describe the model decay we have observed in the online serving environment. And generally, we find that after around 4 weeks, we'll need to do a model retraining to help us to get the performance back to a high position. And then the next section, I would like to share some conclusion and takeaways about our work, about like what we have learned from this project. And here are some key points that we want to share here. The first one is machine learning can be useful. From our experiments, we find that even some very basic models like random forest or XGBoost can give us quite good results. And the second key point is that machine learning jobs usually require some data for training. And especially for infrastructure related problems, we usually have a huge amount of logs. And we find that logs could be a pretty reliable starting point for machine learning jobs. And the last key point is we also need to be really careful in model evaluation. The models should be evaluated on various metrics, not just on the overall accuracy. We need to evaluate the models on different perspectives. And finally, there is some future work that I also want to cover here today. Like say we are trying more sophisticated data discretization approaches to see whether they could help to improve the model performance. Also, at the same time, we are trying more different state-of-art classification algorithms, such as some deep learning approaches. And then there's also about some model decay optimization, because we have observed some model decay issues in the online environment. So we also would like to know whether we can optimize that to reduce the impact of model decay in an online serving environment. And the last thing is about model interpretation, which is quite crucial for an infrastructure problem. That not only we want to get some good results, but also we would like to know whether we can find some patterns or find some rules from the model trained. And this is also what we are doing now to help us to gain some insights from the models. So this is about some future work that we are doing now or what we are planning to do. And this is all about like what I want to present today. Thank you.